300 miles off the Oregon coast, deep beneath 1,400 meters of seawater, the Pacific floor is swelling and shuddering right now, and it is deforming. Real-time sensors record uplift past historic danger levels, and thousands of microquakes are erupting every hour. Yet almost no one on land knows this is happening. Why is this hidden force so powerful? And what happens if it does not stop? Sensors anchored to the ocean floor, powered by a web of fiber optic cables, are streaming back numbers in real time that defy ordinary expectations. Pressure recorders show the caldera at axial seamount has swelled by more than 2 meters since its last eruption in 2015, creeping steadily toward the benchmark that in previous cycles has signaled imminent eruption. Seismometers tuned to the faintest tremors register hundreds of tiny earthquakes each month. Each quake is a fracture, a slip, a sign that magma is pressing upward, forcing the crust to yield. The rate of inflation is not just steady, it is accelerating, with recent months clocking uplift at up to 25 centimeters per year. William Chadwick, who has tracked axial's behavior for decades, describes the situation in plain terms. In 2015, we saw about 2.1 meters of uplift before the eruption. Now we are past that, and it is still rising. The pressure is real, measurable, and growing. On the live data plots, the current curve overlays the pre-eruption line from 2015 and keeps climbing. This is not a theoretical forecast or a distant possibility. The numbers come from instruments wired directly into the volcano itself, updating every 20 minutes. Each new data point narrows the window of uncertainty. Scientists are not waiting for a distant alarm. The system is already in motion. The summit is rising, the crust is cracking, and the signals are clear. The volcano is approaching its known limits. What lies beneath these accelerating numbers is a force with the power to reshape the seafloor, and perhaps far more. Axial seamount rises from the Pacific floor like a hidden mountain range, yet its true scale is almost impossible to grasp from the surface. The summit sits nearly 1,400 meters below the waves, but the volcano itself towers another 700 to 800 meters above the surrounding seabed. Its caldera stretches roughly 3 by 8 kilometers, wider than the downtown core of most major cities. This is not a single peak, but a sprawling complex, its rim marked by steep walls and fractured benches, the scars of eruptions past. What makes Axial truly extraordinary is not just its size, but the source of its power. Most volcanoes draw their energy from a single system, but Axial is fueled by two. It sits directly atop the Juan de Fuca Ridge, a seam where the oceanic plates are slowly pulling apart, creating new crust as magma wells up from below. At the same time, a deep mantle plume, the Cobb hotspot, pours extra heat and molten rock into the system, much like the plume that feeds Hawaii's volcanoes. The result is a dual-engine volcano supplied by both the spreading ridge and the underlying hotspot. This rare combination means Axial receives more magma more often than almost any other submarine volcano in the Northeast Pacific. Its caldera floor inflates and deflates in cycles measured by meters, not centimeters, as magma pulses into the reservoir beneath. Bathymetric surveys reveal a landscape constantly reshaped by these forces, fresh pillow lavas, collapsed pits, and benches that mark the boundaries of previous eruptions. Unlike the dramatic cones of Mount St. Helens or Vesuvius, Axial's bulk is hidden under darkness and pressure, but its potential is anything but quiet. The volcano's restless inflation is not a quirk of nature. It is the visible sign of a system that is always being recharged, always building toward its next event. For scientists, Axial is a living laboratory, revealing how the planet's engine works, one surge at a time. In the late 1990s, scientists tracking the Pacific seafloor began to notice a pattern at axial seamount. The first modern eruption, in 1998, left behind new lava flows and a sunken caldera, but the instrumentation then was sparse. By 2011, a network of bottom pressure recorders had been installed, quietly recording years of slow uplift. When the eruption struck that year, the caldera floor dropped by nearly 2 meters in a matter of days, confirming a cycle: inflation, eruption, deflation, repeat. The 2015 eruption became a turning point. With pressure sensors and seismometers in place, researchers watched the seafloor rise, tracked the swelling magma chamber, and for the first time, used the data to forecast the eruption window. Their model predicted that when uplift neared about 2.4 meters, matching the peak before previous events, the system was primed to rupture. When that threshold was reached, a swarm of earthquakes and a rapid drop in pressure signaled magma on the move. New lava poured onto the North Rift Zone, and the caldera floor collapsed once again. Between eruptions, the caldera slowly reinflates as magma refills the reservoir beneath. The cycle is measured in meters, not centimeters, with uplift accumulating over years and then vanishing in days. Each eruption and recharge period has refined the forecasting model, but the lessons are humbling. The intervals between eruptions have shifted, and the inflation rate has changed pace, sometimes invalidating simple predictions. Scientists now rely on a dense array of sensors, knowing that only continuous, real-time monitoring can capture the subtle shifts that mark the countdown to the next eruption. The history of Axial's eruptions is written in the rising and falling seafloor, and the instruments now serve as both witness and warning system. A network of cables, stretching nearly 900 kilometers across the Juan de Fuca Plate, powers and connects the most advanced underwater observatory ever built. This is the Ocean Observatory's Initiative Regional Cabled Array. From shore stations in Oregon, electricity and high-speed data flow through armored fiber optic cables to a series of primary nodes anchored on the seafloor. Each node feeds clusters of instruments: pressure sensors, tilt meters, seismometers, chemical probes, distributed in and around axial seamount's caldera and vent fields. At the heart of this system are the bottom pressure and tilt instruments. Scientists call them BOTPT. These devices sit directly on the volcanic summit, measuring the weight of the overlying water column with precision down to the centimeter. Even as tides, storms, and passing tsunamis push and pull on the ocean surface, the BOTPT instruments filter out the noise and isolate true vertical movement of the seafloor. Data from these instruments update every 20 minutes, transmitted instantly through the cable network to researchers on land. According to the Ocean Observatory's Initiative instrumentation lead, the array now includes about 150 instruments at Axial alone. Pressure and tilt records from multiple BOTPT sites are compared in real time, allowing scientists to track not just overall uplift, but subtle differences across the caldera floor. These measurements are so sensitive that they can detect the slow year-by-year swelling of the volcano and the sudden meter-scale drops that accompany an eruption. With this infrastructure, Axial Seamount is no longer a remote mystery. Every tremor, every pulse of magma, every shift in the crust is recorded and relayed with almost no delay. The volcano is wired, its inner workings revealed by a web of sensors that leave little to chance. The data are not just numbers, they are the volcano's heartbeat, monitored continuously by the people who know exactly what to listen for. A sudden collapse on the flank of Axial Seamount would send millions of tons of rock plunging down the slope, displacing seawater with explosive force. In this scenario, the first tsunami wave would cross the deep ocean at jetliner speeds, but the Oregon coast still sits nearly 300 miles away. Standard models show that a wave from this distance would take hours, not minutes, to reach land. For the network of undersea fiber optic cables, though, the danger is immediate. Over 95% of the world's internet traffic moves through these cables, bundled along the seafloor in tight corridors. A single landslide or eruption could shear through multiple lines in seconds, cutting connections before any warning reaches shore. Telecom engineers describe the aftermath as a race against time. Repairs in deep water can stretch from days to weeks, while data and emergency calls are forced onto crowded alternate routes. The margin for response is thin, and the consequences ripple far beyond the ocean floor. Emergency planners along the Pacific Northwest know how quickly local disruptions can spiral. When an undersea cable goes dark, internet and phone traffic reroute, but not always fast enough. Hospitals and 911 centers depend on those same lines for critical data and emergency calls. A landslide or eruption near axial could sever multiple cables in moments, leaving coastal communities facing minutes or hours of disconnection and days of slowed international traffic. A regional emergency manager says, "If you lose a trunk line, you lose time." Scientists now watch axial's restless uplift, not just as a volcanic warning, but as a real-time indicator of stress in the Juan de Fuca plate. Some researchers see these signals as a window into broader tectonic forces, unsettled plates that could reshape the region far beyond the volcano itself. The question is not just what axial will do next, but what it might be telling us about the Pacific's deeper unrest. Today, the ocean's hidden forces test the limits of our technology and our preparedness. As sensors relay data in real time, our digital world floats on fragile ground. The next signal from the deep may arrive without warning. We are only as secure as the mysteries we choose not to ignore.